Greetings, everybody. This video will hopefully give you a better idea as to how to approach what I call the Head Start problems. Um, and it's a very standard application of one D motion would cause an acceleration. Um, and typically, as I said, it involves one object where one moving object passes another, or where maybe one moving object is ahead of the second object and the second object either speeds up to catch the object ahead of it, or it might slow down so as to prevent it from colliding with the object ahead of it. And typical real life example one is suppose you're a speeding car, and they pass a stationary or moving police car. Typically, suppose you're going 45 miles an hour in a 25-mile-an-hour school zone. And there's a police car, typically in the mornings during the weekdays. They like to hide out in school zones, and rightfully so. They try to catch a speeder. So the police car is parked. You go speeding past them at 45 in a 25-mile-an-hour zone, they're going to pull you over. But whether they're parked or moving, it doesn't really matter. But the idea is, when you pass them, there's a certain human reaction time. The police car won't accelerate to try to catch you until that natural human reaction time, usually about 2 or 3 seconds. Until that reaction time passes, they don't do anything. It's perfectly natural. So during that time, you're still moving, so you have what's called a head start. And eventually, he sees you, uh, but you're still moving. You're speeding past him. He or she sees you. Uh, it takes them a second or two to step on the gas. That's what's called the reaction time. But during that reaction time, obviously the speeding car is still moving. You have a head start. They have to pull out, and then they have to catch you. They have to chase you down. Another example is, as I said, due to a signalman's error, two trains are actually accidentally put on the same track. The one that is put on the track first is ahead of the second train car, i.e., it has a head start. And typically, the second car, seeing the first car in front, will decelerate, i.e., slow down, so as not to collide. But those are that's what we call them head start examples. Well, what we're going to do is we're going to take kinematic equation one, which I've written here, and we're going to apply that equation to both of the objects. Let's call them object one and object two. You can call them A and B, one and two, E and F. It doesn't matter. I just call them one and two to make things simple. Well, for the head start problems, both objects will start from an initial position of 0. So xi goes away. And so we don't need an xf. We just say the distance that each object travels is x, and it's going to be vit plus 1 half a t squared. Now remember, a could be positive or negative. Remember, if you're slowing down to avoid a collision, you're decelerating. Your a is negative. Now, typically, to make these, not to necessarily make them easier, but to simplify things slightly, let's one of the objects is always going to be moving at a constant speed. Let's call the object moving at a constant speed in the green. Let's call that object one. Now remember, constant speed means two things. V is not changing, so you don't need the subscript. It's always V. Remember, constant speed means it's not changing. There's no initial and no final. It's the same everywhere. Now remember, constant speed means it's not accelerating. It means a is 0. So the 1 half at squared term, that goes away. So 1, you drop the subscript on the v initial. And 2, second, the 1 half at squared term goes away. So for the object moving at a constant speed, x is just v times t. Remember, and we're calling that's the green, we'll call that object 1. Now remember, the object, typically the object has a head start. It could be you pass the police car when you're speeding. You have a head start on the police car. There's two trains in a tunnel. The, the the first train has a head start. You're slowing down so as to avoid a collision, but the object one is going to have a head start. So that head start distance, let's call it d1. So the first kinematic equation for object one, the one that is not accelerating, x is d1 plus v times t. What is d1? That is what's called the head start distance. You pass a police car. He has to, how do you calculate d1? Well, that's the distance you move while during that reaction time. Remember, that's a real thing. It's not an instantaneous thing. You pass a police car, he or she, whether it's a female or male patrol person, it takes them a second or two before they hit the gas and accelerate. That's called the reaction time. During that reaction time, you move a distance d1. You have that head start. How to calculate d1 depends upon the problem, but we'll do some examples. Now, so green, object 1, that's the object moving at a constant speed. Object 2 is the object that is moving at the constant acceleration. So that's the blue. So that's the kinematic equation applied to the accelerating object. X is VIT plus 1 half AT squared. Now for the accelerating object, object 2, the blue, VI can equal 0. If a speeding car passes a stationary cop car, for example. So, in that case, that VIT term would go away. Now, A can be negative. The second train slowing down to avoid a collision. Now, again, consider the human reaction time. We'll call it TR. During the reaction time, TR, the object 2 has not yet begun to accelerate. But if it's moving during that reaction time, it will travel the distance d2. For example, you can pass a moving police car. You could be going 45 in a 25-mile-an-hour zone. There might be an unmarked police car who's moving at the speed limit. So that the police car is moving at 25. You speed past him at a constant speed of 45. So in that case, he has an initial speed. But there's still the reaction time. Again, there's that 1 to 2 second reaction time where he's moving at the speed limit. You go speeding past him. He doesn't accelerate until that reaction time has passed. So we'll call that distance that the accelerating object moves during the reaction time, we'll call that d2. And now remember, both objects move the same distance x, so simply set the two equations equal to each other. You've got, for the object moving at a constant speed, object 1, that's x is d1 plus vt. For the accelerating object, object 2, x is d2 plus vit plus 1 half at squared. Set those equal to one another because both objects travel the same distance x, which is, now our goal is we need to take this equation and we need to solve it for t. Well, what you do is you just using basic algebra, you rearrange this equation so that you have a quadratic equation in t. And the algebra steps are trivial. This is what you get. You get 1 half at squared plus parentheses vi minus v times t plus parentheses d2 minus d1 equals 0. Well, that's in the standard form of a quadratic equation. Ax squared plus bx plus c equals 0, where the uppercase a, b, and c are your coefficients. So in this case, the coefficient uppercase a is 1 half the acceleration, b is the parentheses vi minus v, the constant term c is d2 minus d1. Then you just plug the coefficients, the uppercase a, b, and c are the coefficients, you just plug them into a solver. This is not an algebra class. You all can do the algebra. We don't need to. You might have a solver programmed in on your calculator. There's plenty online. But what you want to do is you want to solve for t, and then you're almost done. But basically, again, the green object 1, that's the object moving at a constant speed. Object 2, the blue, That's the object that's accelerating. So that's the most general equation right there. Now again, if the second object, if object 2 is at rest, for example, if you pass a parked police car, meaning his initial speed is 0, so that term would go away. And obviously he's not moving, so he won't travel any distance d2. That's the rather easy case of a head start problem. But I'll post some videos on these worked out examples. But again, your goal is you've got this quadratic equation in T where the coefficients are the coefficient large A, because again, general form, ax squared plus bx plus c equals 0. The uppercase A, B, and C are the coefficients. A is 1/2 acceleration, B is vi minus v, C is d2 minus d1. Plug those coefficients into a solver to get the time, and then you're almost done. So I'm going to go ahead and save this video and get it posted.